Our group worked on the graph scattering transform, whose members were Rebecca Gini, Mason Nakamura, Sam Smith, and Emily Thompson. In recent history, convolutional neural networks, also known as CNNs, have proven to attain state-of-the-art performance in many machine learning tasks. We worked with the scattering transform, which is the mathematical model of these CNNs, allowing us to use predefined wavelet filters. We apply the scattering transform to graph structured data, producing a sequence of coefficients to each graph. We then use these sequences of coefficients to classify new graphs by implementing a support vector machine for classification. The scattering transform uses a nonlinear multi-layered structure which outputs coefficients at each layer. In our implementation, we use the 0th, 1st, and 2nd order coefficients. We first applied the scattering transform to classify 3 different models of random graphs, specifically the Erdos-Renyi, Watt-Strogatz, and Verbisi-Albert graphs. We found that the scattering transform can distinguish between the geometries of the random graphs quite accurately. And next, we applied our network to a real-world social network dataset, specifically the IMDb binary dataset, which is a movie collaboration dataset of collected movie, actor, actress, and genre information. Each node is an actor, and there's an edge between them if they've appeared in the same movie. The task is to classify whether the network is from the comedy or romance genre. We were able to reproduce and improve upon the results of Gao, Wolf, and Hearn by modifying the graph signals, also known as the signal vectors used. We note that choosing our graph signals as the degree vector d causes us to kill off the coefficients, which we try to work around. Since the degree vector holds valuable information, we navigated this problem by instead using a modified version of the degree vector. In particular, we found that using the logarithm of d as a signal vector works quite well. With this modification, we improved Gao, Wolf, and Hearn's results from an average accuracy of 71.2% to 72.6% over 50 iterations. For real and synthetic datasets, the scattering transform produces a high-dimensional representation of each graph. Therefore, we must use dimensionality reduction to increase the interpretability of the results in a two-dimensional setting. So we use principal component analysis, also known as PCA, to maximize the variance of each dimension. We found that Erdos-Renyi random graph classification retained high variance when dimensions were reduced significantly. This may be caused because PCA is effectively removing noise from the data rather than useful information, which could lead to an increase in performance. For the IMDb binary dataset, the results were more expected, with a decrease in accuracy as dimensions were reduced. For our future work, we will consider other random graph models other than the 3 we experimented with. We will also use graph scattering to synthesize new graphs from a given random graph model. We will also likely experiment on other data sets to see if the modified degree vector is still valid on the signal vector as a signal vector, or if this is a quirk of the IMDb binary dataset. And if it remains valid, analysis on how it works so well would also be interesting. We also experiment on large datasets, especially those previously tested out in Gao, Wolf, and Hearn. We also explore different methods of dimensionality reduction, and a particularly interesting choice would be to experiment with the squeeze fit algorithm, which is a method of dimensionality reduction designed to be used for classification tasks. We would also like to thank Michael Perlmutter, Nathan Bergoni, and Sarah McGuire for guiding us to this research. And this RU was supported by the NSA and NSF as well as MSU.